Hello and welcome to this Edexcel Further Math Statistics 1 video using the central limit theorem. This slide summarises what was covered in the first video in this section, and it may well be worthwhile just pausing the video at this point to familiarise yourself with the information on the slide. The first example we're going to look at actually identifies for you the fact that we're going to start with an original population that's binomial. But again, it may be worthwhile just pausing at this point and reading through the information in the example and noting that nowhere in that example are you given any information that the original population is binomial. The clue that we have that it is binomial is that we're interested in the event throwing a 6 that would have a constant probability of 1/6, and we're throwing 100 times, so n would be 100. We're interested in how many 6s thrown out of 100 thrown. And we can use the central limit theorem to evaluate the required probability, because we are interested in the distribution of the mean from a sample of size 60 that is a large sample. And do be aware that it's quite confusing that we also use n to represent the sample mean, and it's very important that you can identify an n as a parameter for the binomial distribution and an n as a sample size. So how can we find the distribution of x bar? Well, we know our original population follows a binomial distribution with n is 100 and p is 1/6. And from the work you've done on the binomial distribution, you know that the mean for a binomial is np and the variance is np 1 minus p. And therefore we can work out the mean and the variance. And having done that, we then know that the sample mean will be normally distributed with the same population mean as our original population, but with the variance sigma squared divided by 60, the sample size. And on this side you can see that the mean NP has been evaluated as 50/3, and the variance NP 1 minus P gives us 125/9. And remember that it's good practice to leave an evaluated mean and variance in its exact form if that's at all possible. And hence we know our sample mean will be normally distributed with mean also 50/3, but with the variance, the original variance, divided by 60, and this is simplified for you over here. So it's now very simple to work out the probability of the sample mean that can be regarded as a continuous variable, it being greater than 17, because we know the distribution of that sample mean. And the evaluation of a normal probability should be very straightforward for you to find directly from a calculator, or you can evaluate the z-score and use tables if you prefer that method. The second example we're going to look at is quite different, because the first paragraph of the example gives us information about the mean and the standard deviation of salaries for full-time employees in a company. And it's very easy to make the assumption that the salaries are normally distributed simply because we've been given a mean and a standard deviation. However, if you think about the mean plus or minus 2 or even 3 standard deviations, which should cover the whole range of salaries for employees in this company, it's very unlikely that salaries are normally distributed and so the likelihood is that our original population is quite skew. However, we can use the central limit theorem because we're interested in the distribution of the mean for a sample of size 35, which is bigger than 30, and so we can use our knowledge of the central limit theorem and the distribution of the mean in order to find out the required probability. So very simply, in this case, the distribution of the sample mean would be normal, and the mean would be exactly the same as the mean of our original population here, and the variance, and be aware that we haven't been given the variance but the standard deviation of the original population. The variance would be the original variance divided by 35. And it now again just means that we need to evaluate a very simple normal probability. So using a calculator or using tables, you should be able to obtain the probability the mean salary of a sample of 35 employees is below 16,500. So we have looked at a couple of examples here. Do be aware that examples using the central limit theorem could involve any of the distributions that you've already met, or it could involve the mean of a large sample from a skew population, or one about which we know very little. And the central limit theorem is also used extensively in hypothesis testing or in the construction of confidence intervals for an unknown population mean, when we either don't know anything about the original population, or we might even know that that original population is not normal. And that concludes this set of videos on the central limit theorem.